Alright, here we are with the answer key for the practice test for Unit 3, 2.6 to 2.9 in our text. Given some function, k of x, where we know k of 3 equals 5, so we've got a point. Think of it like this. And we know that the derivative at this point is -2. Find the equation for the line tangent to that function at 3. Just a nice little warm-up problem. We know that this is the slope, so we do y minus 5 equals -2 times x minus 3, right? There's my x value and my y value, point slope form, and there's my slope, all right? Use slope intercept form. All right, well then I just got to do some distributing, and I get y minus 5 equals -2x plus 6. I add 5 to both sides, so my final answer is -2x plus 11. All right. Given this function, sketch a graph by plotting a few points. All right. Well, if I make a little chart, x and g of x. This is a square root function. You know that from the beginning of the year. Parent function stuff. 0. Can't do it. That is not defined. But I can plug in 2 and I get 0. I can plug in 6. 6 minus 2 is 4 and I get 2. I'll sneak in one more. How about if I plug in 11 minus 2 is 9 and that gives me 3. So to sketch a graph, I've got 2 targets here in case I make a mistake as by request. So 2, 0 and 6, 2 is right there. And it's just this graph that's going like that. Okay. Then it says, using the concept of slope of a tangent, sketch the graph, the derivative of g of x on the same axes. All right. Well, it's not going to be defined until it gets to 2. At this point, you're going to have a tangent that's going to be near vertical, so it's going to have an asymptote right there, we think. And looks to me like the tangent right here is about up 1 over 2, so about 1/2. So by here it's come down from infinity, it's come down to 1/2 or something like that. And then it's just going to get closer and closer and closer to 0, but it's never going to get to be 0 if it's a half of a parabola. All right, so that's g of x, g prime of x, the derivative. This is g of x right here. All right. Then it says find the derivative using the definition. There's not much space here, so I'm going to squeeze it in. It's the limit as h goes to 0. That is, the definition. That is a goes to, or x goes to a. X goes to a. And I have got then my f of x, which is radical x minus 2. Minus f of a, which is radical a minus 2, all over x minus a. All right, so this one is a straight up rationalize that thing. So I do radical plus radical over radical plus radical. It's just going to be 1. It's always the opposite sign. So I'm going to get the limit as x goes to a of, and here's where the rainbow bits cancel out, and I know it's going to be x minus 2. Then minus a minus 2 all over, that's a, oh no, that is 2, x minus a. All right, well what this then is equal to, that's the limit as x goes to a, and now I can reorder things like I want, and this is a minus 2, so actually there's nothing to even reorder. When I bring that minus sign in, that's plus 2, it just becomes x minus a all over x minus a, and then times the radical plus the radical. Well, these cancel, and I'm left with the limit as x goes to a of 1 over my radicals, which is x minus a plus the radical a minus 2. I said x minus a, but I meant x minus 2. Well then, I don't have the problem of division by 0 when I just take and substitute a in right here. This gives me my derivative, which is radical a minus 2 plus radical a minus 2, which equals 1 over 2 times the radical a minus 2. Alright, so that is it right there. Now I want to say, does that produce this graph down here? Is your mathematical answer similar to what you'd expect your equation to look like? Well, when a gets really close to 2, 2 minus 2 goes close to 0. This gets super small, and 1 over super small does go to infinity. I cannot go anything less than 2 because I still have the same problem of a radical, so that makes sense. And then let's try our point here. When I plug in 6, 6 minus 2 is 4, square rooted is 2, 1/4. Well, I was guessing the slope was 1/2, but really it's 1/4, so it should have been a little bit lower, but other than that it checks out. So I would say yes, this graph looks good. Alright, I could expand more, but I don't want to waste your video time. Finally, what is the equation of the line tangent to g of x at 3? So I plug in 3 right here. 3 minus 2 is 1. The square root of 1 is 1, so it's 1/2. So this gives me a slope of that tangent line of g prime of 3 equals 1/2. So slope-intercept form, I'm going to do the same thing I did up above. I'll just do it right here. I'll say y minus, and if it's 3, I plug in 3 into the original function, and I get 3 comma 1. So when x is 3, it's 3 comma 1. And so y minus 1 equals, and that turned out to be 1/2, then x minus 3, and again I just distribute and put that into slope-intercept form. Y equals 1/2 x. When I distribute the 1/2 in, I get negative 1.5, and I add 1, so it's minus 0.5 or minus 1/2. Alright, so there it is for part D. Alright, that's page 1. Page 2, given the following graph, sketch the best possible graph of f prime of x, the derivative. Alright, this is slopometer stuff. Just start off with the zeros. There's a 0 right there. There's a 0 right there. So you're going to ask yourself, when is the slope of my tangent line 0? And here it's going up. You could even talk about concavity here. This part is concave up. This part is increasing, so I know my derivative is going to be increasing right here like that. Here it's decreasing, so I know my derivative is going to go something like that maybe. And then here the derivative is getting steeper and steeper and steeper, so it's just going to go zooming up this way towards infinity like that. So that's what this thing looks like. And then on this side, similar, that's a steeply negative slope, so I'm down here, and then it's going up to 0, so that's going to go like this, and then at this point this slope just continues to rise and goes like that. Alright, so right here this is f prime of x, my best guess. On to this one, identify which graph is the derivative, the original function, and the second derivative. Well, I see that right here there's an obvious 0, right? So I go down, and that might mean that the derivative of this is this one. All right. Let's just check out some other zeros. It looks like this one here has a 0 right above it that is there. This one here has a 0 that's right below it. So it looks like this then is f, then this is f prime, and this then here is f double prime. Okay? And you should be able to get those with a little bit of trial and error. Okay, on to the final page. It says, given the graph of the derivative, so this is the derivative right here, let's see if we can sketch the graph of the function. Alright, so if this is the derivative, that means there's a 0 right there, and we're told that at 0 it's -2, so I'm going to go down to about -2 and say I know our function goes through here. If this is the derivative of the graph, this means that the slope is negative, getting towards 0. So if the slope is negative, it's going to be coming down like this, and then now the slope is positive, so it turns a corner and is positive. So it's going to be concave up, with that as the local minimum. All right. So then it's approaching 0, getting towards 0, but is not there. So it's going to go up somewhere and then flatten out like that, and then up like this, and then flatten out. And we don't know exactly how, but something like that. All right. So it says then, where is the function increasing? Well, the function is going to be increasing anywhere the derivative is positive. So it's increasing from 0 to positive infinity. Where is the function decreasing? It's decreasing as it gets closer and closer and closer to 0. So it's negative infinity to 0. At what values are there a local max or a local minimum on the function? There is only a local minimum, none, in the local max, but there is at 0, comma, -2. So we're given that. Where is it concave up? It's going to be concave up when we do the second derivative, and the second derivative is positive. So that looks like here we've got a second derivative. The slope is down, down, down until it gets to right here at -2, and then the slope is going to be positive of our second derivative. The slope is positive up until 2. So it is going to be concave up until 2, and then there's an inflection point, and then it goes. So I should fix this. It's going to be concave up to 2, and then switches like that. So f is concave up from -2 to 2, concave down from negative infinity to -2, and from 2 to infinity. All right. So then this one finally, we have got a function that has a derivative that's greater than 0 from negative infinity to positive 1. So 1 out there. And so that means that the function is increasing until it gets to 1. So whatever it's doing, it's going up and up and up and up and up and up and up till it gets to 1. And then it's decreasing from 1 to infinity. So it might peak and then go down after that. So that's going to be a local maximum right there. The second derivative is greater than 0 from negative infinity to -2. So that means it's concave up until it gets to, there's -1, I'll call it, there's -2. So this is going to be concave up until this point, and then it'll be concave down. So I'm going to have that be my inflection point. There's my max, it's concave down, and then it turns to concave up. And it is also concave up because it's greater than 0 from 2, 1, 2. So there's another inflection point, so I got that a little bit better. Now I might have to move this whole thing. There's 2, there's 1, there's -1. Also, it's concave down between 2 and -2. So this is concave down, so we kind of got that. And then it tells us that as it goes towards negative infinity, it's at -3. Well, I kind of got lucky. This was just by chance. I haven't done this problem since last year. So it's approaching -3. There's -3. And then it approaches 0. Wow, I got super lucky on that. And it's going to look something like that. There we go.